Okay, so let's jump into this. So all right, good to go. I'll get your attendance updated, Jeswa. Thank you for joining. All right, so the last stuff we'll go over is testing devices. We walk through everything that we've gone so far. We did identifying faults, specifically faults, short circuit, ground fault, and overload. Then yesterday we talked about overcurrent protection devices and how they can react to some of those things. We talked about resetting breakers, which was the easy part, talked about the fuses and all that, where the fuses live in the disconnect. So now let's get into devices. And I'm just picking outlets because usually with switches, it's not a device that goes bad a lot because, or I should say, anything can go bad, but it's not a device that experiences things like short circuits and overloads, of course, or anything because nothing gets plugged into them that carries a load. The switch is just opening and closing the circuit for the lights or for whatever, but lights in general. So if a switch goes bad, it's usually going bad because of overuse, could be something like that. Not to say that something can't be shorted out in the circuit where the switch is on. Sometimes rare, unless the switch was undersized for the circuit, like somebody put a 15 amp rated switch on a 20 amp rated circuit, which happens, if somebody goes to Home Depot, grabs the cheapest switch, one of those 89-cent switch. I don't know if they're still 89 cents, but they used to be under $1. So you just grab that one because, hey, this is the cheapest one. And those are usually the 15 amp ones. But so if you need a 20 amp circuit, then you can put too much amperage on that switch, and yes, it will damage the switch. So we'll focus on outlets, and we'll talk about 3 types of outlets. But first, let's go with these, which is the ones that you were working on in the labs, and also for my online students today. The troubleshooting lab is these 4 scenarios here with checking, I should say, the troubleshooting lab is checking the outlets for identifying faults on them. So let's go over the 4 that you can test with a meter. All right, yes, you can use a plug-in tester with these, but it's a good idea to understand how to do it with a meter. There are situations in which you do want to use plug-in testers when you're just going through a bunch of outlets and you're just trying to see if everything is working correctly, were things installed correctly, inspections coming in this week, so we want to make sure grounds are all there and all that stuff. Things that could be missed, but if the inspector finds it, then they could fail the inspection. Not that it's the end of the world, they just have to come back and you have to pay again for that. So 1 or 2 or a couple of grounds missing from an outlet can cost a lot of money for that reason. So let's go into the 4 faults. There's a 5th fault, but I'll explain as we just categorize this. And I know I gave you this yesterday, but just a redo for those who didn't catch it all yesterday. So open is how we describe the fault on the outlet. We have an open hot. We'll do open neutral. Then we have an open ground. And then we have the hot and the neutral reversed. Now, usually if you have the hot and the neutral, the ground reversed, that's usually going to trip the breaker because basically you're now ground faulting the situation. And with the hot ground reverse, not so likely because of the green screw that's on the outlet. People usually know that is for the ground. It sometimes gets confusing for the inexperienced person when they have the silver one on one side, the gold one on the other side, and they might not be able to make sense of it. Although these days, if you're buying an outlet and it comes in a little box, usually it gives a good explanation. And they are nowadays, unfortunately, I guess, or fortunately, I don't know how to judge that, but they are kind of set up for the homeowner to be able to replace their own outlets. With some caution, just given breakers got to be turned off and all that. So we're going to just approach these 4. Now, let's start with the fact that, and I mentioned this yesterday, these 2 situations here are not going to have, or rather I should say, the load will not be energized. This is usually how you discover you have one of these 2 problems, either open hot or open neutral, which is somebody's plugged in something to the outlet and the outlet is not, the load is not working. When it comes to the open ground and the hot neutral reverse, not that it can't operate, but likely these things are in operation. And hot neutral reverse, they've been around for a long time. As you mentioned yesterday, open ground, the outlets are just working until you check it. Then you go, oh, there's no ground here. Same thing with the hot neutral reverse. A lot of these old outlets from back when have the hot and the neutral reverse, and people have been plugging in lights, lamps, and standard loads into them forever, and there's been no reason to suspect anything because the loads have been working. So with that in mind, let's now get into what my meter is going to tell me. All right, that's how we know. When the meter shows me a number, now I can approach one of these problems. So we'll start with the hot and the neutral reversed. The open hot and the open neutral situation. And here, when I measure between the hot and the neutral, I'm gonna just write. By the way, I'm just gonna write 0 voltage. Sometimes your meter says something strange like 32 volts or 18 volts or something weird. Only because the meters are just trying to give you a number. Now, the more expensive the meter, the better it is at being able to distinguish when something is not operational. If you just have a standard meter, and I'm not saying a cheap meter, but just a regular meter with, basic operational meter, nothing in the $300, $400, $500 range, then your meter still struggles to just kind of tries to give you a number. It's trying to sense, and there's a lot of little micro things going on inside. So that's why I say the number could be something strange, but it just simply is not 120. So keep that in mind, because it used to confuse me a little bit when I first started to test circuits and outlets and I had an open hot or an open neutral. Mostly it comes in with the open neutral, but I would see a weird voltage and I would just start to run my brain through the things that they've taught me. Is this voltage drop? Is this low voltage? What am I looking at here? And it can get very confusing if you haven't worked with a meter a lot. So in the situation with the hot, with the open neutral, when you measure between the hot and the neutral here again, in both of these circumstances, you get 0 voltage. This is why the load doesn't work. It's not until you do the second test, when you check between the hot and the ground, that things start to become clear. Because in this situation, still nothing, because I don't have a hot. I changed that G a little bit. And in this situation, now I got 120. So these are same, but different. Load's not working, but in one of them, the breaker's good, the power's there, everything is flowing voltage-wise. I just don't have the neutral to complete the circuit. In the open hot, well, that's a different, we'll talk about open circuits in a bit. We'll get into the situations that could, open or give us no voltage at an outlet. But we just proceed in that direction. Look for breakers, look for GFCIs that are tripped, or different scenarios like open wires or anything like that. So they both look the same when we judge between the hot and the neutral, but always remember that whenever you're testing an outlet, we always want to make sure we check between the hot and the neutral and the hot and the ground. Okay, so now going over to the other situation. Here, if I check between the hot and the neutral, everything is gonna seem fine. I have 120, so I'm not suspecting anything. My load's working, but now when I check between the hot and the ground here, now I get nothing. All right, so clear indicator that you have a open ground. So problem, yes, as I was mentioning yesterday, the circuit still works. It is unsafe now for a few reasons: short circuits, for ground faults, for anything like that. We do want to have a low impedance or a lower impedance path to ground so that we can trip breakers quicker. All right, now the hot and the neutral reversed. Here, when you measure between the hot and the neutral, this is why I say it's going to be working, because we still have 120. It's just that the hot is on the neutral side and the neutral is on the hot side, but your meter doesn't know that. It is still measuring 120 volts. When you measure between the hot and the ground, here's where, let me put this up a little bit because we're going to have a third one here. Here is where you see no voltage. All right, hot and the ground in this case are going to give us no voltage. But there's a pause here for a second. Because if we look at the open ground and we look at the hot, neutral, reverse, my meter is telling me the same thing. It's not now if you use a plug-in tester, of course, the little lights shine bright, telling us what's up. So good, you know. Now I'm not knocking the plug-in tester, but it's a good idea to know, or a good thing to know how to do this with the meter in case you don't have it, or whatever the case may be. So in any situation where you're suspecting either hot, neutral, reverse, or open ground, then you do the third test, which is, and this is the only time you do it, which is you check now between the neutral and the ground. All right, let me just raise this up a little bit because of the screen. And here, surprisingly, I will see 120 volts because this neutral is technically a hot. Right? The hot and the neutral were reversed. So I will read 120 now. So now I'm being informed of the situation. Now I know it's not an open ground. Now I know it's a hot, neutral, reverse. Or the other way around. I checked between the ground and the neutral and I got nothing. All right, if you wanted to add that one, that would be fine too. Here you would simply get 0. So, okay, it's an open ground, not the hot, neutral, reversed. Now the other situation here is that if you, this is the other thing you can do option, well, you're going to have to do it anyways, which is you're going to have to open up this device, you're going to have to remove it, and there you also can get a visual check on things. But that's only once you're going to start to get into fixing it. We don't want to approach the problem by removing the, although you can, right? If you don't have a load working on the outlet, like over here, you know, sometimes I like to remove the outlet when things aren't working because, one, I get to do a nice little visual check, see what's going on under the hood, right? See what's going on in there. I have literally seen no neutral at all in the junction box, like especially when conduit is, and you have to pull wires, and believe me, we forget a wire or two. So opening up the device is good. The other reason why I like to open up the device is it gives me access to the actual little screws in there, and I'm an over tester. I overly confirm problems. I have seen too many weird things. So, you know, like for example, I'm measuring between the hot and the neutral inside the prong, like inside the receptacle part. The prongs are going into the receptacle, and I'm getting 0. I have seen receptacles simply just be damaged, where I have power, the receptacle's bad. So that's why I say never with 100% confidence on anything. So here I'm measuring, I got no voltage. I think, you know, again, I also check between the hot and the ground, and I'm getting some weird stuff here, and I assume no hot. And now I start to go into the process of solving this as though I have an open hot or an open neutral, whatever. But it is actually a damaged receptacle. That's not from the terminal points where you've landed the wires to the actual receptacle prongs. You're not getting any power flow. Opening it up and using the screws on the back, it's just been something that, since I've seen too many little weird things out there, I like to do. And then again, you also get a good visual of what's going on back there. Same as I haven't seen a hot, I haven't seen a neutral, but things get forgotten sometimes. All right, I don't think I have anything else here. So any questions following?
I have
yeah.
Question. Could you please repeat the hot and neutral reverse? Why hot and neutral 120 and hot to ground is 120? No, neutral to ground. Why?
Okay, so let's say, all right, so let's I have a hot here and I have the neutral here. If I put my meter here, and here, my meter's going to say 120. My meter doesn't know that the hot and the neutral reverse. It just senses hot, senses neutral, or senses difference in polarity. That's fine. When I then check between the hot and the ground, I'm checking now between a neutral and a ground. Now the meter sees nothing. So then I do the third check, which is between what. Now, some clarification if it is necessary. When I say check between the hot and the neutral or the hot and the ground, I'm not talking about the hot and the neutral wires. I'm talking about the positions on the switch or outlet, sorry, that we call, this is the neutral side. This is the hot one. Yes. So that's what I'm saying. So now when I measure with it where what I think is the neutral point and what should be the ground point, not what I think should be the neutral, what is the neutral point, and now I get 120 because we have a hot where the neutral should go.
Thank you.
You're welcome. Yeah, so that's what we got there.
Wire between the hot and neutral.
Yeah. So power is at the, so everything is good. So this is just a mistake in whoever landed this. Everything is good. We got the hot, we got the neutral, no problem. Now, ideally, we don't like to do this hot. I would, a switch, I have some tricks to do it hot. But I don't like to land on terminal points of or devices, switches or outlets, hot. Like bring the wire hot to the terminal point. I don't like to do that because the yoke is metal. I'm holding on to how else the outlet's not going to float in the air for me. I got to hold it. So if I mess up with this hot wire and I touch the metal, now I can get shocked. So if you want a little tip on how to do this hot, which maybe you're not ready for that yet, but one day you will be.
Yeah, I got shocked that way a couple weeks ago.
Oh, I remember getting shocked. This is how I learned that certain parts of the device is hot. You gotta be careful. I grabbed the whole thing.
Grab the part. The yoke.
Yeah, the yoke it can get energized.
Yeah.
So here's a little trick. This is what I like to do. I'm going to draw everything, even the connection points, right? The little clips that we would break. Here's what you do. First of all, to remove the outlet, right? You got the hot wire. Unfortunately, it's on the neutral, and then the neutral's over here. First thing you do is you cut them. All right, so you take your I like to do the side cutters with this. You know, I don't like to get the lineman in there. I don't like to get my wire strippers in there. I like to do the side cutters. And cut it as close as you can, obviously without touching any metal.
Yeah.
So the reason why you want to do that, I'll just erase a little bit here so that you can have the most wire possible. All right, so now I got this wire over here and that wire over here. And so let's just say I put them in the right order. So now we have the hot on this side and the neutral on this side. So here's the trick. The trick is splice. Not a big, like I didn't discover plutonium here, no big deal. But you just land a wire on the hot, land your neutral on the neutral point. You have your ground as well, right? Land your ground. And now, don't do anything yet. Electrical tape around all of the screw points, making sure I can't see anybody. And now we go in the order that we always land everything. First the grounds, safety first, ground is bonded. Then the neutrals, this neutral and that neutral, there should be nothing there. You're safe so far. And now you only have to worry about one hot splice. And technically you only have to worry about one wire. It's just that one that's hot. So you can strip your end out on this one, strip that out. You have your stripped out end. You have your wire strippers now. Got to be a little bit, again, takes a little bit of experience. You got to make sure your hands are only on the insulated part of the wire strippers. And you just, do the little circle, strip out the insulation. And now you just simply bring the two wires together. There shouldn't be any arcing because, well, there shouldn't be any arcing unless you have something plugged into this and this thing is in the on position. You can have something plugged in. If it's a lamp, turn the lamp off. Or better yet, just unplug everything.
Yeah, I tried to strip the wire.
The hot?
Yeah.
Yeah.
Hot. But I mean, I could have stripped it and been fine, but I was holding on to the device still.
Oh, got it. Yeah. Yeah. So usually if you haven't seen this little trick, one second.
A load in the receptacle and first connect the neutral and ground and the last one put and wire.
Yeah.
Sorry about that. I thought I had my wire strippers nearby. I don't have my wire strippers nearby. But when you're working with a set of wire strippers, right? I'm going to try to do this with my hand. All right. So here's my wire strippers, right? Cut this way. You go around the wire, but here's what you do. Here's the trick. Don't go up, down, cut. Open, go side to side, cut.
Yeah.
And then you turn them. And this turn already separates the insulation. So again, you don't cut straight down, because if you cut straight down, now you're going to be on the copper and you're going to have to do the little spin thing, and here's where your hand's going to have to start. So you cut sideways and you just turn the wire strippers. And as you turn the wire strippers, the insulation that's in the front is going to get pushed forward, and now you should be able to just jog it on out. With careful, obviously, but it is, and you can practice it when you guys get down to the lab on Monday. Just get your wire strippers, hold them sideways, cut, turn, and you'll see it separate the insulation. Better on solid wire than stranded wire, which I don't think you guys have worked with stranded yet. You will next module. All the control labs are with stranded wire. And you'll see a bunch of little strands inside. So it's sometimes a little bit trickier with stranded wire, but usually if you're doing receptacles, it's Romexin. So then put them together and cap it off with the wire nut, and you should be good. And now everything is safe. So now you can hold the outlet. You're a little bit more comfortable. You don't have to worry so much. And now also, as you're trying to get it into the mud ring too, because that's the other thing. Even if you did this great, spliced it live. If you didn't do the electrical tape around it, trying to get it into the mud ring could be a little scary. Hitting the sides, and at least you don't get shocked, but. So there's a trick. Pigtails and splice. Same thing for a switch, and just make sure the switch is in the off position. Okay. Let's move on to some other outlets. Okay. So actually, I don't need those to be that big. These are dryer outlets. They are not the same as the ones used in the oven or the range, but they are the same in the sense that the configuration kind of follows the same pattern. So the one on the left has a NEMA number, and I'm going to also, if you haven't done this yet, or if you have, I'll remind you, just walk you through a little bit of the NEMA number. So every device, by the way, has a NEMA number, right? These are 1520 Rs. These are 1520R, yes. No, sorry, 5. Sorry about that, forgot the number. 520R, 5. The 15 amp one, the one that's just straight like this, is 515R. Okay? So, not so important right now for these, but that's what they are. Now let's come over here. The one on the left here is a NEMA, all of them are called NEMA and then the number, 1430R. And the one here is a NEMA 30R. So
the one left for us is like almost completely black.
Say again?
So
the receptacle, it's okay. It's okay. That's why I'm putting the numbers up, because none of this stuff here is really, and I'll do the prongs on them.
Okay, yeah.
Yeah.
We can't see that at all.
All right, good to go. And then we have the left here. All right, there we go. Cool, cool, cool. There we go. And then we have the left here. All right. Cool, thanks for letting me know. My screen looks, but I guess, yeah, once it's going.
I want to use white.
What's that?
Might want to use white.
White? I don't have white.
Not white?
I can, no, on my pen, no, I can use yellow.
Oh, yeah, that might be better.
Okay, good.
Oh, there you go. Yeah.
Nice. Yeah, you guys have thought this was white? Or maybe it has looked whitish.
No,
Yeah, I only have black, red, blue, green, and then the yellow. But good, if that's translating, good.
White in the color to use. But I guess we don't have white then.
No, yeah, no white on the pen version of it. I guess they figured the whiteboard is the least color that they want to give me is white. All right, so the 5, going back over, and I'll just put it here on the side as a reminder. We had the 15R, and then we had the 520R. So the first number on the device gives us the configuration of the prongs, all right, or of the, these are actually called receptacle points, but whether it's going to be 4-wire, whether it's going to be 3-wire. All right, the first number, what NEMA calls it, it's the catalog number. All right, that's the first number is the NEMA catalog number. The second number is the amperage that the device is rated for. So 15 amps, 20 amp, this one's rated, both of these are rated for 30. And then the R stands for receptacle. So if you were wanting to buy a plug, for example, for either one of these that you see here, I would buy a 1430P for the plug-in or a 1030P for the plug-in. All right, so that's the first thing. And it's important for you guys to know about the NEMA numbers because, like, if you go to Home Depot, there's no problem because you can walk down the aisle and you can do a visual check and you can grab the receptacle you got and the one and just do a visual and go, yeah, these look the same. But when you get into the ordering from a supply house, which eventually you'll be in that arena, right? Ordering from supply houses and ordering outlets from supply houses, you give them the NEMA number. You don't tell them, I need a receptacle that's 120 and there's too many. If you see the NEMA catalog, the categories, it's like a bunch of them. So we skip all that and I just say, I need 5 1030Rs. That's it. And these are the ones I'm going to get here. Now, the ones that are for the oven, they're just a higher amperage, but they follow the same NEMA number. The one for the oven is 1450R and 1050R as well, which I think they have them floating around code B. They have kind of both code C. There's where you do the oven outlet. But I think they also have 30s floating around. They're the same size, so you can't tell by the size. You have to literally look at the NEMA number that's yeah, you guys can't see it, so it's written right here. It says NEMA right there on the side, and it says 1030R on it. All right, so you're looking for that on the outlet. I'm going to get rid of that because I don't need it for that. So you're looking for that on the outlet. Now, let's walk through these devices. Because this is now getting into the practical side of this, because you will at some point have to install one of these or an oven one. So I want you to know how to walk through both of these situations. The 1030R is the older version. The 1430R is the new version. So I don't know exactly when, but somewhere along the years, maybe the 90s, maybe the 2000s, I think maybe in the later 2000s they made it official. All dryers and ovens come with a 4-wire plug. Right, a 4-wire plug. So I'm going to label the 4-wire plug here. This is going to be the hot. That prong there. This will be the other phase hot. The ground is up here, the reverse tombstone it looks like. All right, it's like an upside down tombstone. That's the ground. And this one down here is the neutral. The 1030R was almost the same, except it had the hot. I'll put it over here, or if you can see it, if I draw it on the receptacle here, should be able to. If not, nah, I'll put it on the outside because you guys said you could. That one's the hot. The one on the other side is the hot. And this bottom one was the neutral. But this neutral was also the ground. And when you open up this receptacle in the wall, the ground wire going here, or the neutral going there, was bare copper. Just like, and you know, on the Romexes, they would just run a Romex wire to this because we're in a home. So it would be bare copper neutral. So that can be a little scary for, not for Muhammad, because he was telling me yesterday that all the neutrals over there are bare in his country where he's from, and which is true. If you go to all these European countries and stuff, their neutrals are bare copper, or many of them. I don't know if they've modified and updated, but if you're in America and you're a new electrician these days and you see a neutral that's a wide open copper wire, that could be a little bit confusing, possibly even a little scary, like what's going on here? That thing's going to have a load, but it doesn't have a load. Remember what I was talking about with a balance. If this outlet plugged in the dryer were operating at 30 amps, meaning there's 30 amps on A phase, we'll just call that one A phase, and 30 amps on B phase, there is nothing for this neutral to take back to the panel. So why was the neutral in the dryer situation if it has no job? But it was providing something. And I'll head over to the device here. Inside the dryer and inside the oven as well, there are these components called relays. You might have heard of a relay if you've messed around with your car, or if you work in an industrial setting, then you've definitely heard of a relay. I showed you the coil that goes inside of a relay. You will have relays, you will have relays next module. All right, and the job of this little coil is to actually be energized. Let's say I bring hot to this side, I bring negative, or if it's DC, or neutral to this other side, and this becomes magnetized, where we get the magnetic field. But this becomes a little magnet. That's why it's hollow inside. All right, it becomes a little magnet. There's a little piece of metal here, and there's some contacts in front. And when that gets energized, it becomes a magnet, and it closes the contacts. Right? This one becomes a magnet, and this one gets pushed into it. When these contacts close, things happen. Next module, you'll work with one where we'll start a motor. Or when these contacts close, the dryer motor starts to go. Or when these contacts close, the heater inside the dryer starts to activate. Or the oven, right? You guys get the point. But this coil is not a load. There's no load capacity here. It's just being magnetized. So there's no amperage being produced by it. There is, because we can never say there is no amperage. If there's resistance and voltage, there's amperage, but it is below 1 amp, so for us that means 0. If you were in physics, then you would get down to the micro world and you would give me a number there, 0.0001. For you, that's amperage if you're in physics. But for us, I can't measure that, so it's nothing. So there is no load return on this neutral, even though the neutral is providing a service inside of the... Can't do it with a ground, because the hot and the ground can't make the magnet. Right? I cannot bring a hot to this side and a ground over here. It will not magnetize now. I need that neutral. So, I can erase that. Divide the 30. So, why am I saying all this? Because, and I just ran into it, all right? I just ran into this situation. A neighbor I had asked me to go and change the dryer outlet for them. They said they had an electrical company go out there. Electrical company said $500 to change the outlet and change the plug on the dryer. I was like, wow. But that was good, because now the $300 that I told them was awesome, and I would have done it for $150. But that's why it's always good to let an electrical company go out there and overbid a job, because they have vans and insurance and, you know, the things that they got a lot of overhead. I got nothing. I just got an F-150. So $300 for an hour's worth of work was no problem. But here's the scenario. When I got to the dryer, what I say, modern dryers, you buy a modern dryer, it comes with the 4-prong plug.
They got 3.
On the wall was the old 3. So and it was an older model 3, not even a newer one, but that irrelevant. You are allowed. The reason why I'm telling you is because if you run into this situation, I don't want you to panic. I don't want you. What you don't want to do. What is illegal? What's the illegal part? The illegal part is removing the old receptacle and putting in the new one, and saying, well, Mr. Perez said this was a neutral, and also was the ground, so I'm just going to put a little jumper between here and here. This is highly illegal. All right, I got it on video, which I'm saying. This is no good. This is illegal. Do not do that. We are allowed to still use the old system. It's grandfathered in now. Now, if this was new construction, then no. You have to run the 4 wires and use the 4-wire plug. 4-wire receptacle. But I'm not going to tear out all this wire from the drywall, and then this is now a $1,000 job. So, So on the back of the dryer, where the connection points are, right? When you open it up, on the back of the dryer, you're going to have L1 for one of the hots. You're going to have L2. You're going to have the neutral point in the middle, and then there'll be a little ground screw. The plug wire the 4-wire is plugged into this, so they have the hot going this way, they have the hot going here, they have the neutral connected to the neutral, and they have their ground connected to the ground. But you're going to remove this cord. All right, you remove that cord completely, and the cord you're bringing only has 3. So here's what they tell you. Let me put all this back. What they tell you is this, because there's also a little piece of metal that's connected to the neutral and bonded to the frame of the dryer. So here's what they tell you. If you're going to use the 4-wire plug, you have to remove that little clip and leave it like this. If you are going to use the 3-wire, you are simply going to remove the whole cord and then install your 3-wire and leave that little piece of metal connected to the frame, because your neutral is also your bond for the frame. So this is not very complicated. If I'm making it complicated, it's not. You don't have to. It's all in a great little drawing on the back of the dryer, as long as it's there and visible. If not, you could always Google it and find the configurations. But this is how we're allowed to do it now. We're allowed to change the plug on the dryer, not the receptacle in the wall, and to a 3-wire situation. We get rid of the little ground that was here. We don't have a ground wire anymore. We do not bring our neutral to that one, because the neutral here is doing the coil thing. It's connected to the coils inside and all the things that are going to activate the dryer. So if you run into that situation, now you have at least some idea that you don't have to panic. Maybe you didn't remember all of that, but some idea that, oh, this is something that I can do. But if you remember nothing else, just remember this. Don't change the outlet, change the cord to the 3-wire. And then, from there you can go forward and try to find if you still need to see the configurations and all that. Now, this is the same for the oven. That's why I don't have the oven here. It's just the same 4-wire situation, 3-wire situation. And I really don't know why the code, I guess I know why the code book did it. They wanted to provide an insulated neutral to the, again, lower impedance path to ground is always best when possible. So 4-wire, and I don't even know what year it happened, but 4-wire became the standard now. All right, now I want to show you one more outlet, because we like to talk industrial a little bit in this module. So there is one more outlet to point out. And again, I know you cannot see these configurations, so I will show you. All right, it looks like that. It looks like this. It looks like this. And then it's got a little situation like that. This is three-phase. All right, this is a three-phase, but it has a name. Does anyone know what kind of receptacle this is called? Twist lock. All right, this is a twist locking receptacle. The idea is when you put the plug into this receptacle, you twist it and it locks in to where now you can't pull it out. So it's used a lot in industrial machinery. All right, it's used a lot when you have, like, for example, a cord coming down from the ceiling and you have your plug end here and you got a machine and you're about to plug it into this. So it's good to do twist locks in that case because the weight is not going to pull the receptacle off. So this is a three-phase system, and now absolutely never, ever, ever a neutral. So this is simply going to be hot, A phase or B phase or C phase, doesn't matter, and hot on the other side with the neutral in the center. Sorry, never a neutral and I write neutral. With the ground at the bottom there. So this is hot, 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 or A phase, B phase, and C phase, and then now the number on this one, all right, the number on this one is, and I think it is the 4. If it's the 4, going back over, if it's the 4, it's 14. All right, so this one is a 14. Is this one 14? I believe this one's 15. Just because I don't think they overlap the same numbers. I believe it's 15. That first number is not the most critical. This one happens to be 30 amp R, but the thing that separates the twist lock from any other device is that it'll have L1530. So it'll have an L in front of the number. All right, so if you ever see the L whatever, you're looking at a twist lock receptacle.
Is the L for lock?
Yes, the L is for lock. Very good. I'm trying to pull up. Home Depot is always best because they let me zoom in on stuff. And because there are some other ones, there is the 4, so let me just walk you through a few of them. And here, you should be able to see that one a little better when because again, Home Depot allows me to zoom in here. 1 second as the picture comes up, and I can go ahead and, there we go. Right, you can see the configurations there a little better. Or probably not, yeah. No worries. More so, I just wanted to give you the name here, right? So we have our 30 amp, 3-phase, flush-mounted, ground locking outlet, or twist lock for the more correct. Not crazy expensive, it's only, normal outlet number here. But it is 3-phase, and then they do have one that's a little bit different where you have the 1, 2, and only 3 of them. This one is an L, so you might be able to see that one a little better.
Yeah.
Yeah.
L630.
L630, yeah, right? So always the L is the identifying feature of the twist locking device. All right, they sell these in 20 and they sell these in 30. They might sell these in 50. Yes, they sell these in 50 as well, although I don't think Home Depot carries them. And then you have the plug system as well, and there's the plug device. So, not that you always have to do this, but anytime you're ordering some of these, you do. So yeah, Home Depot does not offer the 30, the 50, but anytime you're doing some of these, you sometimes do want to buy the plug end with it. I wanted to go to the specs here and see if they give us the NEMA number. Yeah, here's the NEMA number here, L630R. Let me go in a little closer on that one. There you can see. And then it's 250 volt rated. Very likely, if you're using 3-phase these days, you're probably working with 208. 250 is just the overall for that one, right? Grounded. And yeah, there's nothing else really here to look at. But there's the NEMA number for that one. Yeah. So it's just maybe an outlet you have not seen before and you didn't know was in existence, but it is used a lot in industrial machinery. And so it's a good idea for you to know that they're out there. If you ever run into one and you have to replace one, it's like, oh, what is that? I've never seen this before. So now you've seen it. And this one doesn't have the specs, the 31. It's not showing me the specs here. Yeah. I wanted to know if it was a 15. I guess I can zoom in on this one myself. You guys might not be able to see it, but I wanted to see the NEMA number on that one. Yeah, L15. I was right. Yeah, L1530. And believe me, I didn't have this memorized. I just did it this morning and used it. So, all right. Now, here's the last thing I want to say about checking devices that have 2 or 3 phases on them. All right. Same thing as I was talking about yesterday. Just a reminder from yesterday. We'll go back over to this one, say for example. When you have your meter, all right. Yes, you can check between the hot and the neutral. And let's say it gives you 120. And now I check between the other hot and the other neutral, and it gives me 120 again. But be careful, because that might not mean 240. You always want to check between the hot and the hot to make sure you have the difference between the phases there. Especially on an outlet. Like I was saying yesterday with the breakers. No funny business in the breaker because it's just kind of hard to do that inside of a panel. Panel has fixed bus bars and can't really move things around. But as I was saying also yesterday, somebody could potentially run a single phase breaker to here, another single phase breaker feeding this one. They happen to be the same from an A phase position on the breaker on the panel and from the A phase position on the panel. And now when I measure across the hot here, I'm not going to see 240. I'm going to see 0 or something, again, something weird from the meter. So all of these things have to be done anytime you check an outlet. I check between the 2 hots. If it says 0, don't just assume I got no power. It could be another weirder problem. Check now between the hot and the neutral, see if you're getting 120. And don't go, oh, I'm not getting 120, definitely the breaker. No, now check between the other hot and the other neutral. Always see everything. Don't walk away not having numbers to all of it. I never assume anything. Same thing with the 3-phase. And here, as I was mentioning yesterday, we want to do all 3 of the combinations. The A to the B to the C, and the A to the C. We want to establish we get, let's say, 208 between all 3 of those measurement points. Because weird things happen. All right. Any follow-ups? I think I'm good with the receptacles. Okay, let's move over into the last problem, and then we'll get into short circuit calculations, and then we'll wrap up. I am going to walk you through the homework a little bit just to clarify things. And then we'll wrap up for the day. So, the last problem that you can have. So, when we started troubleshooting on Monday, maybe you came into troubleshooting thinking, troubleshooting is hard. There's a lot of things going on, but we've really narrowed it down to some really simplified problems that can exist on a circuit, which is breakers tripped. Only 3 things could have caused it: short circuit, ground fault, or an overload. Now, with the short circuit, depending on how it's wired, you could have the short between the hot and the neutral, between phase to phase. In the checking with the overload, we could have discovered a bad breaker versus the circuit is overloaded. If we have fuses, we replace fuses. We know how to test the fuse. So, not that you have all this, but you have some direction now to go in. So the last problem you could have is the customer. Let's just say the customer. The customer says there is no power at the outlet. Right? There's no power there. And how they're telling you there's no power there is they didn't check it. Whatever they plugged in, it doesn't work. So you approach the receptacle the way we just did. Grab the meter between the hot and the neutral. No voltage on my meter. Okay. Check now between the hot and the ground. No voltage on my meter. What you are now looking at is what we call an open circuit. So first, let's just define what that means. An open circuit is no voltage at the load. But we're going to unpack that a little bit because it is an open circuit in this module, no voltage at the load. When you get to the next module, that's going to be a little bit more It's going to have a little bit more to do with that. And I am going to explain a little bit. I'll show you some control circuit and we'll just elaborate a little bit on it. But we're talking circuits now, not control circuit. We're talking regular circuits. So no voltage at the load. All right, at the load. Not anywhere else. At the load, I have no voltage. And again, not guessed, seen it on my meter. Nothing between hot and neutral, nothing between the hot and the ground. So establish that I have no voltage at the load. Now, whatever the load is, if it's an outlet, I've checked the outlet. If it's a motor, I've checked the motor connections. If I'm at a machine, I've checked the machine, no voltage there. So before this is where I see some people struggle in where do I go from here? No power. So anytime you see no power at the load part, the first thing you want to do is to check voltage at the source.
Which actually is
And I'm going to call it the power source, although I don't always like to use the word power when I'm talking about voltage because it kind of indicates wattage, but that's for this, it's good to say it that way. So I'm going to check voltage at the power source. Now, what is the power source? I don't know. If you're in a home, then there's no option. It's a breaker or a panel. All right, if you're in a commercial building, it could be one of the many panels they have, but eventually you'll find the panel. If you're in an industrial setting, now power sources can be a little bit different because you have control circuits. Control circuits are fed through low voltage, step down transformers that convert into some very low voltages. Even these days, even more so, they're getting stepped down into DC voltage, which you have to go through a inverter. It's called a power supply in the world of motor control, but it is simply an inverter. Converts DC to, rectifier, AC to DC. So whatever the power source is, for now we'll just say a panel, I have no power at the outlet. I want to go and make sure that I'm starting with voltage. And then when I get to the panel, tripped breaker. Now I know how to go into my trip breaker situation. Reset the breaker, trips fast, ground fault or short circuit, and then go through the short circuit ground fault steps. Trips over a long period of time, well, maybe something in this outlet or circuit is overloaded, right? So we know how to approach a tripped breaker. But this is the confusing one. The confusing one is no power at the receptacle, there isn't a single breaker that's tripped. Everything is on. Right? In other words, I have power at the power source, but I don't have it at the load. And this can be sometimes a little bit scratch your head, what now situation. But there is a easy way to approach this. And the way I'm going to write it here is you want to do a point to point check. All right, you want to simplify this circuit. You want to narrow down all of the points between all of the possible places where this circuit could have opened. All right, so extra note if you want to write it down, an open circuit is not a fault. Open circuits don't necessarily trip breakers. An open circuit, I'll give you a scenario where no breaker will ever trip. Breaker, GFCI, next outlet, I'll just put GFCI. Next outlet fed through GFCI, GFCI tripped. Breaker's going to be on, but I got no power at the load. So check power at the load, no power at the load, walk over to the panel, breaker's good. Okay, point to point now. Residential, it's a really good idea, especially these days. Start thinking GFCI immediately. Now, older homes too, you can also think switch, right? Switch on the wall. Usually people know that they have a switch that feeds an outlet, but maybe not. Newer home, they haven't gone through everything. You're there because they are going through that punch list. They just moved in, they can't get this outlet to work, and you figure out that one of the switches on the wall is the one that turns on and off the outlet. So it can be simple, it could be difficult to find an open circuit, it could be a wire nut that's come loose, it could be a, you know, sometimes, and which you should never do, is somebody fed through the receptacle, right, to the next outlet, not a GFCI, but just a standard receptacle feed through, and one of these plexes got damaged. All kinds of little things can happen, but if you ever run into a situation where at the load there's no voltage, first establish that you have power at the source. Don't start checking anything else. Don't start running around looking for GFCIs. Don't start looking for wire nuts that are open or outlets that have gone bad or anything. Go to the source. Establish voltage at the source, and now you can do point to point back towards the load. Now, that is a, not a trick, but a thing or set of steps or a common sense way to approach control circuits. All right? This is something that people who've worked with control know how to do. So a lot of times electricians will work from the loads back towards the panel. And that's not a good thing to do, because when you work with control circuits, that could be a very, very long route before you get back to that power source. And then you get back to the power source and there's no power at the power source. So you just wasted a bunch of time going through a bunch of stuff to then figure out it was the power source the whole time. So here's a control circuit. All right, and I think I've shown you this one before, just to go over a few things. And when I remember earlier I said relay, that's what that CR stands for. It stands for control relay. Now these are not the components. These are representing the, you'll get all familiar with symbols next module. These symbols, these little circles, represent the coil, the one I just showed you, in the control circuit, that when they magnetize and close the contacts, things get energized. So first you have to energize the coil, then the contacts close. And to point out a few things, that is a contact connected to that control relay over here. And so is that one here down there. So there's 1, 2, 3 contacts, and a contact looks like that. And if you don't know what the component is yet, no worries. Just understand that when this thing closes, now voltage can flow through. All right, it can go on to the next thing down the line. While that is in the open position, voltage is not going through. So the first thing that has to get power here is that relay coil, and then this will close, all of these at the same time, and now these things get power forward. But you'll notice I run into another open situation here. So that coil here closes this one. This coil here closes that one. And then finally, after all of that, which by the way happens instantly, because that's how electricity travels, then motor 3 starts. Okay. Let's say I got called over to the machine because motor 3 has not started. Motor 3 hasn't started yet. Okay, I'm going to erase all this. And what do? I bring my meter, I check voltage between the 2 points of the coil, and I got nothing. So you can do this in one of 2 ways. You can go here and see if you have voltage, and then you can go here and see if you have voltage, and work your way. Well, 2, let me go check 2 to see if it has voltage. Nope. 1, let me go check 1 if it had, nope. Let me go and work your way that way. Or you can simply go, all right, let me check to see if there's power even coming into this circuit. And now once I establish that there is power, if there's no power coming into the circuit, great, I got the problem solved. I mean, not solved, but I got what the problem is, and now I can go around fixing things. Maybe that little fuse is blown, whatever. But if I do have power, there is power going in, now point to point. What is the first place where that power lands? Well, the first place it lands is here. Do I have power there? Yes, no? Okay, on to the next thing. Power there, yes or no? Yes, all right. And we go on through until we find the point where something has happened. Now, this is not a conversation in control circuits, So I don't want to get into the things about the coils and the contacts not closing or whatever the case may be. But this is the point-to-point approach. Now you might be saying, well, hey, this is going to take a while. Yes, but it was going to take a while anyway. I just now am going through the process confident that voltage is in the circuit. Whereas if you were working your way backwards, you still don't even know if voltage is here. So let's just keep it simple now, going back to a regular. By the way, by the time you get done with next module's control circuits, a regular circuit is going to seem very simple. This is what happens when you do controls for a long time, or even just a good 5 weeks of it. A regular circuit is going to seem simple because there's only a panel. How many things can be point to point now before I get to the load? Not so difficult at that point too. So point to point just simply means going through the possible places where the circuit could have opened. All right. All right, any 811, we got one last thing to go over, and it should be fairly quick, but it is some math. So any questions out of this? All right, let's look at the short circuit calculations. This short circuit calculation is first to establish what size does that interrupting rating of the breaker have to be. All right, reminder of that one is going back over to our breaker. As I said, 30 amps is the rating of the circuit, but then there's this 10,000 that's there. So a breaker is selected for that 10,000 based off of the calculation that I'm going to show you now. This calculation needs to take two things into consideration. All right, here's our transformer. We'll do step down. There we go. So what this calculation needs to consider is what kVA, right, what wattage capacity does the transformer have? So I'm going to give us a number here, 25 kVA. And then it wants to take into consideration what the secondary side voltage is. All right, what the secondary side voltage is. However, if it's a 240 volt circuit like a house, the calculation actually only is done on one of the phases, not both of the phases. All right, the calculation is we're only concerned with one of the phases. I mean, something to know, but at the end of the day, I'm just going to give you a bunch of numbers anyway, so whatever numbers I give you, you'll run the formula through the numbers. But that's how it actually goes down. Now, this 120 that you see there has a name, which is different only because we're now talking this, but it's the same as Ohm's law, it's the same as everything, and it's E secondary spelled out like that. All right, and this is again the secondary voltage of the transformer. So the formula is Ohm's law. It's just written different. It's kVA divided by E secondary. And what we do when we do P over E, we get I. I is just written a little bit different. Just want to make sure I'm not in the way. No, I got space. It's I secondary. All right, so I'll just put these little notes here. Feel free to write those as well. And this just simply means the secondary side of the transformer's amps or current, however you want to write that. I'm writing amp just to shorten the space. So this is part one of this formula. This formula is a two-part series. So the first thing you have to establish is what is the possible secondary side amperage of this transformer. So let's run the numbers, right? We have our numbers to do Ohm's law. 25,000, that's 25K, 25,000, divided by 120 equals, happens to be 208. All right, but this is amperage, not voltage, and it is an unfortunate number, but don't get confused. We're talking amperage now. So on the secondary side, potential, this is nominal, meaning we've only done this in calculation form. Will this house have 25,000 watts? No way. This house is going to have only a couple of things on during the day, and likely will never, just like a 200 amp breaker for the house, you measure the breaker, the phases, you're not going to have 200 amps or anywhere near it. You might have 80 at most during the normal process of the house, because the oven's not on while the air conditioner and the dryer and the, all the lights are on, everything plugged into all the outlets. This is why we do all that derating. The second half of this formula, part 2, is I secondary multiplied by 100 and then divided by the impedance of the transformer, and it is represented as IZ, or sometimes you'll hear them call it IZ. All right, and this is simply the impedance of the transformer. All right, just a quick breakdown on what the impedance of the transformer is, because it's irrelevant to us. This is a transformer manufacturer problem, not our problem. But the impedance of the transformer is how much percentage is lost between the magnetic field on the primary side and the magnetic field on the secondary side. There is never 100% energy transfer from the primary to the secondary. Nothing in the electrical world can do this. All right? Like a light bulb. Light bulbs back in the day, 100-watt light bulb just to get X amount of light. Nowadays, a 10-watt light bulb gives you the same amount of light, because we're just becoming more efficient at energy in versus energy out in making light bulbs. Transformers the same way. There is simply just a percentage loss in that system. So on average, you don't have to write any of this down, but little transformers, the ones that are like, let's say, converting 120 to 12 volts, are going to have an impedance of about, an energy loss of about 0.5%, maybe 1.5%. It's very low. A really giant transformer for a big industrial place that's, say, converting 12,000 volts and stepping it down to like 480, this will have something about 8.5% energy loss. All right, you're working with big numbers now. For a home, 4160 to 240 on average, or maybe 12,000, all depends. Somewhere around 2.5% energy loss, 3.5% energy loss, depending on the manufacturer of the transformer. Again, this is a transformer manufacturer problem, but all we need to know is what is that number so that I can do this calculation. So let's throw one in here. All right, let's say it is 3.5. Now, I do want to say this. This is a percent, but when you go to do the math here, do not move the decimal the way you would normally treat a percent. Right? Like if you've ever made bread, the water percentage, or the salt too. If it says 2% salt too, well, when you want to calculate that, you have 400 grams of flour, you have 2% that you want to add in salt, but you don't, you go 2%, you go, all right, decimal 0.02 when I'm going to go make this calculation. Right? Same thing if we have 80%, we go 0.8 when we do an 80%. However, with this one, we do not do that to the 3.5. We use the number as it sits. All right? Again, don't make any percentage conversions here. So now we just plug in the numbers. We have 208. Multiply that by 100. So that becomes 20. Where can I write it that you guys can? I'll just write it over here. All right, we'll come over here. Yeah, 20,800, easy math. And then divide that by 3.5. All right, and we run those numbers too, 2800 divided by 3.5. We get 5,942 IRC. All right, this is in-rush current. So in the event of a short circuit with a transformer this big, with the secondary side voltage of 120 and specifically an impedance of 3.5 on the transformer, you will expect to get somewhere around 6,000 amps rushing into this circuit in the event of a short circuit. So the interrupting rating of the breaker, and I'll put the note down here, must be larger. Now, by the way, larger by any amount. However, there is a cost factor that starts to get into buying a breaker with a crazy high interrupting rating. So that's why you see, what do we have here? 25,000 kVA is about average for the transformer that's feeding a home. 120 is, of course, the voltage that we have feeding the home. And 3.5 is actually a little bit high. That transformer is probably going to be sitting around 2% impedance. But that's why you see 10,000 kVA so common throughout all breakers.
Where did you get 3.5?
I threw it in. It's just a given.
Okay.
Yeah, it's just a given. And by the way, when we go to find the 3.5, it's on the transformer itself, name plate information. So the transformers tell us. But almost like the transformers you guys used did not give us the impedance of it, because it's not a thing we're doing with that transformer. It would be a transformer outside or one of the bigger ones, and kind of gets a little bit out of where we're looking. So these are the formulas, and now let me just walk you through the homework so you just get an idea of how you're going to approach the home. The quiz is just multiple choice, shouldn't be an issue running through the multiple choice. The homework is the one that's going to be short circuit calculations. So let me just pull it up here and let you guys get just a window into what it's going to look like. So you can see the first question here. It says calculate for I secondary. So I'm just asking for the amperage with a secondary voltage of 240 and a 100 kVA transformer. So you run through the numbers there. The next question says, using that answer that you just got, right? Because what you got is I secondary, so using the I secondary and the transformer impedance of, there's the 3.5. Calculate the interrupting rating of the transformer. Now, this question here is going back to yesterday when we lost the ohms, but now I'm giving you an ohm loss. So I'm looking for a number here based off of circuit has 12.5 ohms with a voltage of 120. What would the amperage increase to if the resistance dropped to specifically that number that I'm giving you there? All right, follow-up question just like that one is the last one there. And the one right before it is select the correct size breaker interrupting rating. All right, and this is where you got to remember that note there. Must be larger. So when you calculate this number, you got to find an interrupting rating that's larger than the number you calculated. For example, if this was a multiple choice situation with that number and I told you 4,000 Ka interrupting rating, then no, it's too small. This one's 5,942. So 6,000 would be fine, 7,000 would be fine, 10,000, which is the one that they make. Now, if you run into anything problem-wise, the video will be up. You guys will be able to see it. Also, if you run into any situation, just email me and I'll walk you through something if it has to be. Other than that, we are done for the week with troubleshooting. All right. Next week we'll start on some new stuff, low voltage fire alarm systems. If anyone has any extra questions, as always, please hang out. I'll answer them. If not, you are all free to go. Have a great weekend. I'll see everybody back here on Monday. Stay safe and come back unharmed.
Thank you.
Thank you, guys.
That's insane.